And so to session, I think it's number 5 now of the MQ stream. And Gwydian's going to talk about some internals. And over to you.
Okay, thank you, Mel. So my name is Gwydion Tudur. I work in the MQ development team, normally at IBM Hursley, but as you can see at the moment, I'm working at home. So I've been in the MQ development team for a number of years now, and several of those years I spent working in the MQ4 zOS development team. And this session is going to be looking a little bit into the internals of what goes on inside that black box, which is the queue manager. And hopefully that will be interesting for quite a lot of you to know what goes on inside the queue manager, but also looking at how the queue manager actually works helps us to design our applications so that they perform better, because they take advantage of what MQ is optimized to do, how it's optimized to work. So what we're going to do is start off with what the queue manager actually is, what sort of work it's designed to process, and so on. We'll look at how applications call into the queue manager to perform their work, and then we'll actually take a look at some of what goes on inside the queue manager in what's known as the resource manager. So those are the bits that inside the queue manager, the components of the queue manager, if you like, that look after different logical components of resources that the queue manager needs to deal with. And we'll look at how messages are stored on private and shared queues, and finally take a little look at the channel initiator. So we'll start off by looking at what the queue manager is and what it's meant to do. And by the way, I should have mentioned, I'm happy to take questions in the chat at any point. So if you have a question, just put it in the chat. You don't need to wait until the end. So queue managers, they're essentially to manage resources such as queues and the messages on those queues. And applications, of course, connect into the queue manager to put and get messages on those queues. Now, we do have a saying that we've used for a number of years now, that MQ is not a database. So it is worth comparing and contrasting the differences between how MQ and databases work, because if you consider messages and information in tables in a database, they're actually kind of different. They're used for different purposes by applications. So messages are fairly transient. They reflect the flow of data. So an application puts a message to a queue and it might be moved to another queue manager, but then another application will come along and get that message off the queues. And that should all happen in normal situations fairly quickly. So we don't expect messages to live particularly long. Obviously, if there is some sort of problem where the message can't be delivered immediately, then yes, MQ will take care of looking after that message until it is actually able to be delivered to the application where it's meant to go. But ideally, messages shouldn't be living in MQ for very long. If you think about databases, on the other hand, they usually reflect the endpoints of application processing. So they're stores of data where the data should be living for a reasonably long time, especially compared to the lifetime of a message. So they are different in terms of how applications use them. And if you look at consider what applications normally do with databases and queue managers in terms of what operations they perform on tables and queues, normally most calls to a database are to query information that's stored in a table. So that returns information from the database to the application, but it doesn't actually change anything. Of course, applications can also make updates to information that's in tables, so they can insert or update information to a table, and that does change the information that's stored in the database. But those operations are normally relatively few compared to the number of queries where applications just get to look at the data. And databases can be optimized for that, so optimized so that it's most efficient when there's a lot of applications looking at the data, but only few applications making changes to the data. If you contrast that with how applications use MQ, then what applications do when they're connected to the queue managers is to put messages onto queues, and that of course is changing information that's stored by MQ. It's actually writing information to a queue, and they can get messages and off that queue, and that also changes information that's stored by the queue manager because it's destructively getting a message. Of course, you can browse messages on the queue, but again, that is not going to be the majority of MQ get operations on the queue. Most of them will probably be destructive gets. So you can see that many more operations here that take place to a queue are ones that actually change information in the queue manager. And so the queue manager needs to be optimized to work as efficiently as possible with applications that are with several applications probably that are concurrently accessing queues and updating the queues at the same time. So the queue manager is designed to allow as many applications as possible to concurrently access resources that are stored by that queue manager, and to do so allowing the best throughput that we can for all that work that's going through the queue manager. Now, something else that's very important that the queue manager has to do is to maintain the integrity of transactions, because MQ lets applications perform work under transactions. So an application can do several puts and gets, for example, and if those are all within the same transaction, then the queue manager will ensure that either all that work takes place or none of it does. So that's one of the key principles of what a transaction is. And it's the ability to perform transactions as well as the feature that MQ has, which is persistent messages, which are messages that MQ makes its best, very best to look after. So pretty much guarantees that if a message is put into MQ, then it will be delivered to where it needs to be delivered. It's the fact that MQ has that quality of persistent messaging coupled with transactions, which means that it can give the quality of service of once and only delivery of messages to the application that needs to get those messages. Because the other thing that the queue manager needs to do is to provide an API for applications to be able to call in and put and get messages to queues, and as well as the operations that you can do using the MQI, which is the interface that application use to call into the queue manager. And now you can write applications in lots of different programming languages to call into MQ and run them in lots of different environments. This isn't an exhaustive list of environments that you can use to call into MQ here. For example, you could also have added, or I could also have added the REST API now, which is something that we've added to MQ in recent years. But the REST API is just an application that runs inside a Liberty server and then connects into the queue manager. And the point there is that whichever environment applications are running in, be it ones that I've got on the screen here or the REST API, for example, the way that they call into the queue manager is basically the same. And by the time the request gets into the queue manager, it looks exactly the same to the queue manager, regardless of where it's come from. And that's because of the way that applications call into the queue manager. So when you build an application, you link it with a stub, which is provided by MQ. And that's a tiny bit of code, essentially, that just provides an endpoint for the MQI calls, such as MQ open, MQ put, that those applications will need to call. And so that's why you don't have to recompile your application whenever you upgrade MQ, actually, because that MQI stub is tiny. It doesn't change very often, if at all. It's compatible with different versions of MQ. So you can still call into different versions of Queue Manager without having to recompile your application. So the stub then calls into what's known as an adapter. And the job of the adapter is to change that request into a standard form. So regardless of where or what environment the application is running in, the adapter will change the request into a format. It's known as the QRPL. That's the name of the control blocks that stores the data. that gets passed into the queue manager. And that's a standard control block that the adapters for lots of different environments will convert the request into before passing it into the queue manager. So by the time the request gets into the queue manager, it's in the same format, essentially, regardless of what environment the application is running in. And there were different adapters available for the different environments that your programs can be running in and call into MQ. What happens then when the adapter calls into the queue manager is that it uses the PC instruction that is part of the zOS instruction set, Z hardware instruction set, and that allows the application to switch into the queue manager address space and run inside the queue manager address space while it's performing the work needed to do that MQI call. Now you'll notice that we have the channel initiator here, so I'll just point out that as far as the queue manager is concerned, the channel initiator, which is a separate address space, is essentially just another application. So if you have a MQ client, for example, running on another system somewhere that's connecting into this queue manager over the network and then through the channel initiator, that request comes in to the channel initiator, maybe a MQ put to a queue. Channel initiator processes it and then calls into the queue manager, essentially using exactly the same mechanism as any other application that's running locally to that queue manager to call in and then perform that MQ put. So let's have a look at what's actually going on inside that box of the queue manager. So queue manager is comprised of several different resource managers, and those resource managers all call each other in order to perform the operations that are needed in order to put messages to queues, get messages from queues, and do all sorts of other background tasks that are needed to look after the resources. Now there's a number of different resource managers. We'll look a little bit deeper into some of them later on in this presentation. But just as a few highlights, we have on the top left there, all MQI calls coming into the connection manager. So we will look at the next slide actually in the connection manager in a little bit more detail. But essentially, it's where all the calls from your applications come in. They go into the connection manager, but then needs to call the message manager in order to perform the MQI request. Both of those might call the security manager to perform security checks. Now, the security manager doesn't actually hold a user registry or any list of permissions itself. It calls out to RACF or whichever security manager you're using in order to do those security checks. So there's a lot of talking between resource managers and also occasionally some external systems as well happening here in order to perform each MQI call. Now, the other thing to mention here is that some of these calls are more expensive than others. We will look at this in a little bit more detail later, but we've got MQ Open and MQ Con and MQ Connex, those highlighted here. They are reasonably expensive calls compared to the other MQI calls, such as put and get messages of queues. And we'll look at the reason behind that a little bit more in a couple of slides' time. And also remember that the channel initiator is nowhere to be seen on this slide, because this is all the resource managers that are part of the queue manager address space. The channel initiator is a completely separate address space and just calls in essentially to the connection manager, calls into the queue manager to perform any work that it needs to do, such as putting and getting messages from queues. Now, the connection manager, as I said, is essentially the first thing that applications call into when they call into the queue manager. It's like the front door of the queue manager. So all the requests to perform any work on queues, open a queue, put a message to a queue, and so on, they all come into the connection manager. And of course, any request to connect to the queue manager as well comes to the connection manager. And there's actually enough complexity to deal with the number of connections that are coming into the queue manager looking after them for their lifetime, and also dealing with the termination of tasks that might be connected into the queue manager, because the queue manager might need to roll back a unit of work, for example, that's in progress if the application unexpectedly goes away while it's connecting into the queue manager. So that all needs to take place and is managed by the connection manager. It's not just applications that might be connecting into the queue manager via the connection manager. You might also have an external transaction manager connecting in. If you're doing two-phase commit units of work, that's coordinated by some other sync point coordinator. So you will have that connecting in as well to the connection manager, and then committing or backing out units of work by calling the right verbs in the queue manager. The connection manager, of course, does deal with those things, those aspects that are specifically to do with the connections itself, but a lot of the other work it just passes on to the other resource managers. So it doesn't deal with storing messages on page sets at all. It doesn't deal with logging changes that are made when putting and getting messages to queues at all. It doesn't do any of that. It simply passes on the MQI call to the next resource manager, which will deal with that. And the next resource manager is usually the message manager. The message manager is probably the resource manager that is most closely linked to what applications do, by which I mean, if you think of an MQI call that an application does, such as MQOpen or MQPut, the message manager is conceptually what deals with that MQI request. Now we will, of course, have to call various other resource managers in order to do everything that needs to be done to finish performing the work that's needed for that MQI call. But the message manager, it is what essentially deals with the MQI request itself. And it will get past the MQI calls via the connection manager for pretty much all the MQI calls that your application performs. And then it will do quite a number of things in order to perform those MQI calls. So, for example, for an MQOpen, it will need to validate that the MQI call is correct. So there's a number of options that you can specify for each MQI call. So it will need to validate that all the options that have been specified on the MQOpen are valid, for example. It will then need to resolve the queue. So you will have a queue name specified for your open. That queue might be an alias queue. So it's the job of the message manager to then resolve what the base queue name that is pointed to by that alias queue actually is, and then actually open that base queue. It will have to call another resource manager, the lock manager, to get a lock on that queue maybe. So that's what prevents more than one application from opening the same queue for exclusive input. It will also need to call the security manager to perform a security check to make sure that the application user ID is actually authorized to try to open these queue. So that's a number of things that need to take place just to open the queue, and they're all taken care of by the message manager, although of course it does call other resource managers sometimes to delegate some of that work. There's a number of other things that it does that's quite related to MQI calls from applications. So it deals with triggering, for example. We will look at triggering in more details in a couple of slides' time. It also deals with applications that are getting messages off a queue and going into a get wait, because they want to wait for a message to appear on that queue. So it's the message manager that deals with posting those applications and giving them the message when it actually appears on the queue. So the message they have been waiting for has appeared on the queue. The application now needs to get it and be woken up. Other things that the message manager does are to deal with all the MQSC commands. So these are the commands that can be issued from various sources in order to do things like define, alter, delete objects such as queues, name lists, processes, and so on, all the objects that you can define in the queue manager. So regardless of where those commands have come from, they eventually end up in the message manager, and it's the message manager job to make sure that the updates happen to the objects. And if it needs to, it will, if it's a cluster command, for example, it will put the message on the cluster command queue, so that it then gets processed by the right component. So as we're looking at the message manager, it's worth having a think about, or having a look at some good practices with regards to how your applications use MQ. So now that we've looked at what the message manager does and what the message manager does that is fairly expensive, you can draw some conclusions about how to write better applications, possibly, that are more efficient, or at least which MQI calls to maybe avoid doing too often to make your programs as efficient as possible. So I used the example of MQ open on the last slide to show you the number of things that it needs to do. So it needs to validate that the request, that the options in the MQ open are all okay to start off with. It needs to resolve the queue that's being opened. It needs to locate the object, which is be on a page set somewhere. It needs to perform security checks, all those things. That all makes MQ open quite an expensive operation. So you don't want to be doing it too often. If possible, try not to open and close queues very often. So ideally, if there are several messages that need to be put or got to or from a queue, then you need to open the queue, leave it open while you perform those put and get operations, and then only when you don't have any more put or get operations to perform on that queue should you be closing the queue. So that avoids going through the cost of opening the queue too often. Now, if you've only got one message to put to a queue, we do have the MQ put one verb, which is equivalent to doing an MQ open, MQ put, and then an MQ close. And that's more efficient than calling MQ open, MQ put, followed by MQ close, because after all, the application is only doing one MQI call with MQ put one. It's only having to call into the queue manager address space once. But you should only do that if you're only putting a single message, because it is still less efficient to do MQ put one than to do, for example, MQ open and then two MQ puts and then an MQ close. So the takeaway point here is that opening a queue is expensive, and try not to do it very often if you can, so avoid opening and closing a queue too much. I mentioned triggering slides ago, because this is one of the things that the message manager looks after. So triggering is a feature in MQ where you can define a queue so that if a message, or when a message is put to that queue, the queue manager can put a message to another queue with the goal of being able to trigger an application to start to process that message that was put on the what's known as the application queue, the real message that needs to be processed. There's a way of getting applications started in order to process messages that are appearing on a queue. Now, of course, there is a cost associated with that, because essentially it's almost doubling the cost of putting a message to a queue. Not quite, of course, because it's not an extra MQI call. It's not an extra persistent message being put, so it is cheaper than the actual messaging that's taking place by the application, but there is a cost associated with it. And you can, on your queue definition, choose several different times when your trigger message is generated. So you can say whether you can choose whether you want your trigger message created the first time a message is put to a queue, so that's when the queue depth goes from 0 to 1. You can choose to have a trigger message generated for every message that gets put in the queue, or you can choose to have one generated when the queue gets to a certain depth. You do need to take a few things into consideration when you're choosing which one of those options is best for you. We do have some guidance, I think, in the Knowledge Center for that, but in general, taking into account that it is a cost to produce an extra trigger message, Usually the best way to set it up is to use trigger first, so that when the queue depth goes from 0 to 1, you get a trigger message produced, and then your application that's processing that queue should process all the messages on the queue, and then maybe terminate so that it gets started up again when another message appears on the queue. Or maybe you should go into a get wait and wait for another message to appear on the queue for a little while. That depends on how often you're getting messages putting on the queue, so what your message rate is on that queue. So it is a little bit complex to actually know what the ideal solution there is, but rule of thumb, you should use trigger first, probably. Something else to consider is whether you're getting specific messages from the queue rather than getting just the first message from the queue. So often applications just want to process the first message on the queue, which is going to be the oldest message on the queue. But messages also have pieces of data with them, such as the message ID and the correlation ID, that an application that's getting the message can request the queue manager to return a message with a specific identifier. So a specific message with a specific correlation ID, for example. Now, you can tell the queue manager to index a queue, which means that in memory, the queue manager will keep references to where the messages are on the queue with specific message ID or a specific correlation ID. And that makes it a lot more efficient to get messages with specific correl ID or message ID. Because if you don't have an index, and the queue manager has to go down the queue, essentially scan down the queue until it finds the message that you're looking for. And that takes time and uses CPU, so it's not very efficient. So if you're getting messages by getting specific messages by message ID or correl ID, then you really should consider indexing the queue. And actually, the queue manager these days, if it detects that the queue manager is having to scan down the queue to look for a specific message, will output a message in the job log to remind you that maybe you should be indexing that queue. There's a similar consideration when you're using message selectors. This is where you can specify on your MQGet with a little piece of text that looks a little bit like an SQL query, that you want a message returned where, for example, it has a property that says color equals green, for example. And in this case, you can't index a queue to with a message selector. You can't index a queue to make the gets by message selector go faster. So the queue manager will need to scan the queue to find the message that matches your selector. So that does cost CPU. It might mean that you do extra IO as well. So try to avoid that if the queue that you're getting messages from is deep. So just a few performance tips there that are related to essentially how the message manager works. So the message manager, as you remember, is what deals with the MQI calls from the applications, but it doesn't actually deal with storing the messages itself. It's a data manager that deals with mapping messages and objects to buffers where they're actually stored by the queue manager. So you'll probably know that object definitions, that's queues and topics, name lists, so on and so forth, they're all stored on page set 0. And then the other page sets, the other 99, are available for you to store message data on. Now, each page set has a space map that the data manager looks after, and this tells the data manager which bits of the page that are used, which bits of the page that are free. And the other thing that's on this slide is that for the message page sets, the page sets 1 to 99, each queue is actually implemented as a number of sub-queues. There's actually 20 sub-queues. Why is that? Because each queue can store messages with different persistence, and different priority. So a message can have a priority that is a number between 0 and 9, so 10 different priorities available. And there's also different persistence. So a message can be persistent or it can be non-persistent. So separating messages by priority makes it more efficient, essentially, to put messages with different priorities, and separating them by persistence also makes it more efficient, partly for the same reason, also because non-persistent messages don't survive the queue manager restart. So when the queue manager is restarted, all the non-persistent messages in the page sets can be marked as deleted quite easily because they're on different sub-queues to all the persistent messages. It's also the data manager's job to ensure that logging takes place of updates in the page sets. So it will ask the log manager to write records whenever any changes take place in the page sets. And the other thing that we've got going on in this slide is that we've got the scavenger task. And that's part of the data manager that goes around freeing up pages that are not needed anymore. So they will be pages that used to contain messages, for example, but that message has now been got or it's expired, so it's not useful anymore. We don't always delete the information in the page set synchronously because that would slow down the getting of the message. Instead, the scavenger task goes and clears up a little bit later, asynchronously. So before we move on to any more resource managers, it's worth taking a look at what the key technologies are that the queue manager has to use in order to enforce transactional consistency and also to do that in the most efficient way possible. So the queue manager needs to write to 2 persistent stores of data, essentially, in order to make sure that your messages are safe and your transactions are consistent. And those are to page sets and to logs. But for efficiency, access to both the page sets and the logs are both buffered. So when you put a message as part of a transaction, even if it's a persistent message, queue manager will write a log record because it's a persistent message that's being put, but it won't ensure that that log record is written immediately to disk. So it will go to a buffer essentially before it's written to the disk, because that log record doesn't need to be written to the disk until the point that this unit of work commits. That's the point where the queue manager makes sure that the log record has been written to the log. It does enforce this log write-ahead protocol, essentially, which means that any updates to the page sets have been logged to the disk before they take place on the page set. But the buffers for the log do mean that you don't need to wait for an I/O to the log to happen, for example, for every MQ put of a persistent message. That does make your application go faster. Similarly, with message data, those aren't written immediately to the page set either. So your message data will get written to a message buffer by the buffer manager that I think we'll look at in a slide or two time. And those stay in the queue manager memory for some time. And if you've got a message that stays on the queue for a little while, then eventually it will get written out to the page set. But if your messages are pretty transient, they don't stay on queues very long, then it's a good chance that your message won't actually go to a page set at all. And that's the ideal situation, actually, because obviously accessing memory is a lot faster than accessing disk. So for best performance, you don't want your messages to be being written out to the page set at all. You want to be putting your messages to memory buffers and getting them out of the same memory buffers, rather than having to write them out to disk and then read them out from the disk again. So that's the ideal situation. It's a buffer manager that the buffers for the message data. And what it does is when you get a message, for example, it reads information from a page set, reads the message data from for those messages that are being got out of the page set. It's a little bit clever in that it tries to read information from the page set ahead of when the application actually wants it. the data is hopefully already there in memory by the time the application is performing the MQ-get and wants to get that message data. I should say, actually, when you define your page set, so you'll use this define PSID command that's on the right-hand side of the screen. You specify your page set number, and you specify also a buffer pool. And so that is how you link your buffer pools essentially to buffers. So you will also define your buffer pool with this define buffer pool command that you normally find in your CSQ1 data set. That's command that's run by the queue manager when it starts up. And you can also give it a size, and there's various other parameters that you can actually give the define buffer pool command. When an application puts a message to a queue, then it's actually writing data into the queue manager. So what happens then is that you've got some pages that are containing data that needs to be written out to a page set. So those are called dirty pages because they have data that has not been written out to persistent storage. And those don't necessarily need to be written out to the page set because, as I said before, maybe those messages won't live in MQ for very long. Maybe they'll be put to the queue and then got from the queue very quickly. And that's the best situation because the put and the get will just be using information in memory to put and get those messages. If those messages do hang around for a little while on the queue, then after a few checkpoints, the queue manager or the buffer manager will force out those dirty pages to the page set, so that the information in the page set doesn't get too far behind what's in the log, essentially, so that if there is some sort of problem and this queue manager was to disappear, when it restarts, there's less recovery work to do to bring that page set up to date. Now, a number of years ago, queue manager pretty much only used information that was below the 2 GB bar in its address space. So only information that could be addressed in 31-bit address, in the 31-bit portion of its address space. These days, we've moved quite a lot of information in the queue manager address space up above the bar, so into the 64-bit area of the address space. So there's various bits of data that I haven't talked about that have gone above the bar, but the important bit here is the buffer pools, because the buffer pools are probably the biggest chunk of data that there is in the queue manager storage. And if you look at what the queue manager address space looks like below the bar, then you haven't got an awful lot of space really for the buffer pools and the data to all live there below the bar. You've probably got a maximum of 1.6 gigs for buffer pools, probably a lot less actually. So that means that there's a cap on how much space that you can allocate for your buffer pools, which obviously has an impact because, as I was saying in the previous couple of slides, you want there to be enough buffer pool space available to hold all those messages on your queue that are going to be got soon. Because you don't want messages to be written out to disk because you've run out of buffer pool space, only to be read in again a minute later. So since MQ version 8, I think, you've been able to allocate your buffer pools above the bar, so in 64-bit storage. And what that means is that you can have much bigger buffer pools now if you need to do that in order to make your application work more efficiently. So you really should have enough buffer pool space available to hold all the messages that are short-lived messages on your queues. And that really will make quite a big difference to the performance of your applications if increasing the size of the buffer pool means that you no longer have to be performing I/O to page set in order to put and get messages. It also means that you're freeing up space below the bar for other storage as well. So it just reduces the storage constraints on everything. And we really are recommending that you move your buffer pools above the bar now in your queue manager. Another thing to mention on the subject of efficiency, this isn't really related to the buffer pool, to the buffer manager, but I couldn't think of a better place to put this slide, so it's here. It's about sync point frequency, so how often you call commit essentially from the applications, and how many operations, puts and gets, you have within those transactions. So when you perform an action, putting or getting a message within a transaction, then that means that you have some locking. We haven't looked at the lock manager. That is the part of the queue manager that has to deal with locking. Essentially, because updates that are made within a transaction are not visible to other applications until the point that the transaction is committed, the queue manager has to ensure that that actually happens by locking resources until the transaction is committed. It ties up a number of resources if you have a transaction that goes on for quite a long time and has a number of messages in it. So for each unit of work, you shouldn't have too many messages in it. We've got, as a rule of thumb here, 100 short messages, or maybe even one large message. That essentially prevents your application that is doing a big unit of work from affecting other applications, because that can happen. So try to keep your units of work small if possible. So moving on to how messages are actually stored on queues, you can see that we store messages differently depending on how big the messages are. So the page sets are carved up into pages that are 4 kilobytes in size. And if we have a short message that is 4 kilobytes or less, then it's able to fit in one page. So that's very simple. It gets a little bit more complicated as the messages get bigger. So a long message or a very long message needs to be stored with pages that are, rather than containing message data, they contain pointers to other pages that contain message data. And you can see that the longer the message is, then the more indirection there is, essentially, and the more pages that an application that is getting those messages needs to traverse in order to get that message data. So not only can putting large messages to a queue cause a large amount of data to be logged, so that's increasing your I/O and CPU usage. Also, getting those messages also is going to be slower than getting a small message, and I mean that you might have more I/O as well. So smaller messages are more efficient is essentially the story that you can take away from here. Now that diagram was for how messages are stored on private queues. So those are queues that are only accessible by the queue manager where they're defined, so a single queue manager. And that's all that you have available on distributed platforms. But on zOS, we also have the concept of shared queues, which are queues that are available to more than one queue manager. As long as those queue managers are all running on the same sysplex and are all defined as part of the same queue sharing group. Now, a shared queue, as it's known, the queue itself is available to all queue managers that are part of the queue sharing group. Also, the same messages on those queues are available to all the queue managers in the queue sharing group. So it's really the highest level of availability that you can get for the both the queue and the messages on those queues. And the way that's implemented is that MQ makes use of the cupping facility, which is a feature, it's essentially a special piece of software that runs on the Z hardware. And it's able to provide various functions to make it a lot easier for applications such as MQ and other exploiters to use the cupping facility to share data. So it deals with the aspects of making sure that concurrent updates are safe, for example. What MQ uses is known as a list type structure in the cupping facility in order to store messages on shared queues. Now, the part of the queue manager that deals with anything to do with the cupping facility and shared queues is called the cupping facility manager, as you can imagine. So if you open a shared queue, then it's the cupping facility manager that deals with that eventually, or you put or get a message to a shared queue, then it's also the cupping facility manager. Also, some unique features to do with QSGs and shared queues is, and this is enabled by the fact that we use the cupping facility to implement the shared queues, is the feature that members get notified of failures of other members in the queue sharing group. So if one queue manager in this queue sharing group, for example, was to disappear, then the remaining 2 members would get notified that that one member had gone away. And they would be able to then recover or complete any transactions that were in flight on that failed member, so that those messages become available again on the queues. So if we had a transaction that was in flight, for example, that had got a couple of messages from a shared queue, and then the queue manager went away before completing that transaction, then one of the other remaining 2 members would be able to roll back that unit of work, or at least roll back the messages that were moved by that unit of work by the failed queue manager, roll back those messages on the shared queue. That's made possible by the fact that the cupping facility notifies other members of any failures, and that everybody is able to see that shared queue and make updates to messages on that queue. So this is how we store messages on the shared queue. It looks a little bit complex. So the list type CF structure that MQ uses is comprised of a number of list headers. So these are the entries in the table here on the left. And each list header essentially relates to a specific queue, a specific shared queue. And it holds all the messages that are put onto that shared queue. Now each message, you can kind of see down the bottom right-hand side of the slide here, each message has obviously data associated with it, but also it has a number of bits of information that the cupping facility allows MQ to set. And one of those is the key. And the message key is used by MQ to order the messages on the queue. So the message key will contain the state, whether it's committed or uncommitted. It will contain the priority of the message at the time that it was put and the queue manager that put it. So you can see that by using that key, we can order that queue. Just by ordering the keys in ascending order, we can have the message on that queue ordered in the time that they were put and in priority order. Now, when messages are got from a queue, they're actually, rather than being deleted immediately from the CF list structure, they get moved to another list header, which is a special one for uncommitted gets. That's just in case we need to back them out later if the transaction backs out. So it's in case of moving messages around within the CF structure rather than deleting them immediately. And that's all made possible by the operations that the cupping facility allows MQ to use. So it has operations, some of them actually listed on this topic, on this slide. There are a lot more than this, more complicated ones, but it lets us write entries in, which is essentially putting message to a shared queue. Lets us read entries, which is browsing a message in a shared queue. Move them, which is doing a destructive get, so it's moving a message to the uncommitted get queue, and so on and so forth. There are more complicated ones as well. Also monitoring, for example, that's the last example we have there. That's how we can implement a get wait on a queue, where the queue manager gets notified when something happens on a shared queue, such as a new message arriving. Now, it's not strictly true that all messages in a shared queue are stored in the cupping facility, because due to the constraints of the cupping facility and how MQ uses it, the largest message size that can be stored in the cupping facility list header itself is just under 64 kilobytes. So you can put messages that are bigger than that to shared queues, but MQ will need to store the message data somewhere else if you do so. Now, for a number of years, the other place that MQ would store the messages was DB2, but there's obviously a cost associated with storing message data in DB2. It means that essentially MQ has to call out to another subsystem, then insert some data to a DB2 table, and then do a commit in DB2. So you can see there's an overhead associated with doing that. So in, I think, MQ 7.1, so it's quite a number of years ago now, MQ implemented this other way of storing large messages on shared queues called SMDS. It stands for Shared Message Data Sets. And the way this works is that each queue manager in the queue sharing group has a SMDS. And that SMDS stores the data for large messages that have been put by that queue manager. So in this example, you can see step one, when an application puts a large message to a queue using queue manager 1. Step 1 is that message data is written to the SMDS. In step 2, we then write into the CF structure, so into that list header. Instead of writing the message data, we actually write a little pointer. So we write some data that says the message data is actually in the SMDS for queue manager 1. And then when another queue manager wants to get that message, it looks in the CF structure, sees that pointer, and then goes off and reads the actual message data from the SMDS where it's stored, even if it's another queue manager's SMDS. It's fine for any queue manager to read another queue manager's SMDS, just not change it. They can read, but they can't write to it. So that's how SMDS works at a very high level. So that's all I was going to say about the queue manager. So we'll briefly look at the channel initiator. I think we've got about 8 minutes left, so we should finish up just about on time. So when we were looking at the queue manager, we broke down the internals of the queue manager to the different resource managers that logically look after different areas, different resources within the queue manager. Within the channel initiator, it makes sense to look at it in terms of the different tasks that run within the channel initiator. So each task running the channel initiator looks after a different area or a different aspect of the channel initiator and what it does. So we have the supervisor task, for example, which is one of the first tasks that gets attached by the job step task, and that attaches a number of dispatcher tasks. And it's the dispatcher tasks that actually do the work of a channel when it starts up on the channel initiator. And you can control the number of dispatcher tasks, as you can control the number of several of the other tasks as well. And there's guidance for setting the right number of tasks for your workload in the Knowledge Center, I think, as well as the MP16 performance report that we have. Also, you might want to look at some of the SMF data and the statistics for how busy your channel initiator are before tweaking the number of any of these tasks. And I've got an example of that coming up in a couple of slides' time. So an example of some of the other tasks in the channel initiator you have the adapter tasks. So these are the tasks that perform all the MQI calls on behalf of the channel initiator. So if a channel needs to put a message to a queue, for example, because a message has just arrived over a channel, then the dispatcher task that is running that channel will call an adapter task in order to do that MQ put. You've also got a name server task, which deals with any name resolution for host names. And you've got a number of SSL tasks. They're still called SSL tasks, even though you should be using TLS these days. just as all the parameters in MQ are still called SSL, even though we've moved on to TLS these days. There's some things that we just can't change. So all work to do with TLS or SSL handshakes will take place under those tasks. Also, the encrypting and decrypting of data that's being protected using TLS will take place under those tasks. So it might be interesting to look at a little bit of the life of a channel. So consider how a sender channel gets started, for example. There's two ways that can happen. So first is that a start channel command can be issued, and that can be issued from several places. It can be from the console, it can be the MQ Explorer, or these days the MQ Web Console. All those methods of issuing the command eventually end up with a command being put under the system command input queue. And that'll be a command saying, telling the queue manager that you've issued the start channel command. Of course, the command server runs in the queue manager, but the queue manager isn't what starts the channel, it's the channel initiator that starts the channel. The command server in the queue manager needs to actually put that message, put a message to the system channel in its queue to get the channel initiator to pick that up and actually do the work of starting the channel. When that happens, it's the supervisor task that goes and starts the channel on a certain dispatcher task. And when the channel starts up, it gets allocated to a certain dispatcher task, and that is the dispatcher task that runs that channel for the rest of the channel's life. A single dispatcher task can run multiple channels simultaneously. So you'll probably find a number of channels running on a particular dispatcher, but also you'll have all the channels that are running on your channel initiator hopefully fairly evenly distributed between all the different dispatcher tasks that you have. And the other way that you can start a sender channel is by triggering. So you can set your transmission queue definition to trigger, to put a trigger message to the system channel in a queue when a message arrives on that transmission queue, so that a message arriving on the transmission queue causes a channel to be started to pick up that message and send it in a very similar way. The way that a channel is actually started once that message gets to the system channel in the queue is the same as when you were starting a channel with the start channel command. I'm going a little bit faster now because I realize there's not a lot of time left. For receiver channel, you don't need to issue the start channel command. The fact that a connection comes in via the comm subsystem, that could be TCP/IP, for example, comes into a listener task, and that then starts a dispatcher to do the work that's associated with that channel. I will skip over these couple of slides over normal operations of sender and receiver channels, and instead go on to the channel initiator SMF data. So the queue manager, as well as the channel initiator, writes out various bits of statistics and accounting data to SMF. The channel initiator data came in a few years ago, I think maybe version 8, so it's widely available now. So the statistics give you a fairly high level view of what's going on in a channel initiator. The accounting data gives you more low level information about what goes on a particular channel. So the number of messages that a particular channel has dealt with, for example. As an example, you've got the adapter task statistic report here, and that shows you the number of requests that each adapter task has dealt with. And you can see how adapter tasks allocated on a first free one basis. So when a dispatcher task needs to perform some MQI task, to put a message to a queue, for example, it just picks the first free available adapter task to do so. So you'll see that the top one is a lot more busy than the bottom one. And in this case, we've got the last one having not performed any requests at all. So we've got probably the right number of adapter tasks here. If you were saying that they were all busy, then maybe that would be a case for adding more adapter tasks. The other thing you'll notice here is that the average CPU time for the adapter task is a lot lower than the average elapsed time. That's fairly common because if you consider what request the adapter tasks to, then they call into the queue manager, and they might perform things like an MQ commit, which will block for a little while, possibly, while waiting for I/O to happen, while the commit takes place, and that might mean waiting for data to be written out to disk. So I think I'm out of time now, and I'm actually very close to the end anyway. So in summary, we have looked at a little bit, at least, at how the queue manager and the channel initiator work, what goes on inside them, and how messages are stored on private and shared queues, and also covered some tips for how to design your applications to best make use of how the queue manager has been designed, or at least optimized to work. And are there any questions? Hopefully that was useful to everyone. I haven't seen any questions come in the chat. Feel free to please submit your session feedback using this QR code.
Well, thank you everyone, and yes, please do fill in the feedback. You can either scan the Q code or use the BYOA panel. And so, thank you, Gwydion. Excellent presentation. Yeah,
No problem,
you're getting a lot of accolades. Okay, the next MQ session will be next Tuesday at 3 o'clock, and that's about MQing containers. So I hope to see you at that session. Okay, goodbye, guys.
Okay, thanks everyone. Bye.
Thank you, Gordon.